Oh, right. I see that. Good. So everything works.
So this is the last session, right?
The last session. Two talks and then a discussion. Start. Okay. Okay, I think we are ready to go. Almost perfectly time. So I give the challenge to Lisa. And the first, okay. So.
Thank you. Hi, Stella, can you hear me? Hi, can you hear me?
If you are speaking, Stella, we cannot hear you. Maybe.
No, we cannot hear you.
Okay, sorry, that was my bad. Forgot to push the button. Hello.
Okay, so well, our next speaker is Stella, so I think everyone is here, right? So maybe you can go ahead whenever you want.
Okay, thank you. So, good afternoon from Greece. My name is Stella Fragouli, and this is the work that was performed by the group of Virgo at AUTH, and also part of my master thesis, which was supervised by Professor Tefas. So the table of contents of my presentation, a little things about reduced order modeling, then our baseline model, which was inspired by the works of Kahn and Green, and then the exploration that we decided and the ideas that we tried out and the contributions that came out of our work. So our goal was to construct the surrogate model, and for this reason, we followed the same process as described in the work of Field et al. We used waveforms from the SEOBNR V4 model of non-precession spinning black holes with a mass ratio in range from 1 to 8, and the range of the two spins from -1 to 1. Then, using routines from the ROMPy library, the greedy algorithm and the empirical interpolation were implemented in order to produce a final basis from which we could then reconstruct the initial waveforms. The three datasets were constructed, one for training of 200,000 samples and another two with 30,000 samples for validation and test. Following the work of Kahn and Green, like I said, in order to deal with the challenging interpolation in 3 dimensions, artificial neural networks were implemented to map the 3D input of lambda to the coefficients of the empirical interpolation. We also divided the problem into 2 parts. So instead of working with a complex form of waveforms, we worked separately by dividing the amplitude and phase, which yielded better results. And so several bases were constructed for a number of greedy tolerances from 10 to the -6 till 10 to the -16. And our findings are similar to those of Kahn and Green. And we see that for more strict tolerances, the number of coefficients for both the amplitude and phase increases. And here we also see the mismatch between waveforms reconstructed from the empirical interpolation and the original waveforms as downloaded from the SEO-BNR-v4 model. We chose the bases which correspond to 10 to the minus 10 greedy tolerance. Here I have marked it with a blue color for to highlight it, which was our ground truth for all experiments. So as first step, of course, we aimed to reproduce the results from Kahn and Green with the architecture that we were going to see afterwards that they proposed. And so we obtained a mean square error of 10 to the minus 7 for the amplitude network and 10 to the minus 8 for the phase. Each experiment was performed 5 times in order to measure the mean and standard deviation of each metric. In table 3 down, we see the corresponding mismatches between the reconstructed waveforms from the predictions of the neural networks this time and the original waveforms. And everything was calculated as far as the mismatch is concerned using the match method from PyCBC. So here's a schematic representation of the architecture of our network. We have 3 input nodes, which correspond to the lambda parameters, and then 8 output nodes for the phase network and 18 for the amplitude case, which correspond to the number of coefficients. And in between, we have 4 hidden layers. So, but instead of just 20 that I have plotted here for a more smooth visualization, we had 320 nodes. It's a fully connected network, of course, and it's a number of regression. And here are the learning curves from the 2 baseline networks from the training process for both the training and validation dataset. So we see that they converge at about 400 for epochs for the amplitude and 800 for the phase network. And like I said, we have a 10 to the minus 7 MSE for the amplitude and 10 to the minus 8 for the phase network. And here we see the mismatches with values above the 95th percentile of the mismatch. So in practice, we see the 5% worse cases. On the left, there is the one from the comparison of the reconstruction from the empirical interpolation coefficients and the original waveforms. And on the right, we have the comparison. Oops, sorry about that. And on the right, we have the comparison from those that were obtained from the predictions from our own networks against the waveforms, from the original waveforms. So then the next goal was to improve these results and go beyond the baseline model. So here's a list of ideas that we tried out. So there are 3 distinguishable categories. First one involves the addition of an extra parameter of some of physical meaning, and in this case beta. And what is special about beta is that different combinations of mass ratio Q and the spins of the 2 black hole components, they lead to the same waveforms. So we thought that the introduction of beta to the network would aid the learning process of the network. And then move on to the second group of ideas instead of the augmentation, either on the input like in number 2 or the output like in number 3. So the main idea is that we push our networks to learn by using different paths to reach the same destination. So again, with this trick, we aid again the learning process. And the final group of ideas was that of dissection. So either the input or the output were divided into smaller groups in order to focus on certain range of features. And specifically, like in number 4, this dissection happens along the range of the mass ratio Q, which I remind you was from 1 to 8. So we dissect this range. And in the case of number 5, instead of having a network that makes predictions for a different number of coefficients, instead we end up with a number of networks, each corresponding on a single coefficient. So, and this is the dissection of the output. So here we see the violin plots of the mismatch for all the different ideas that I mentioned. We see that there's an improvement in all cases, except for the case of the network per coefficient, the last in the green one. The reason for this is that because when separating the coefficients from one another, we lose the asset of correlation among them, which then the network cannot make use of during the training process. And the second and major contribution of our work included the implementation of a second network, which is trained on the errors from the first network. So what we essentially gain from this is that a correcting component, which is the predictions for the errors that I mentioned, which helps to improve the final results in training and in the final mismatch as well. So now we see the comparison of the plots of the mismatch, first without and then with this residual network. And we can observe that this time, the distribution of the mismatches resembles that of the ground truth and the empirical interpolation from the start of my talk. So this same trend is observed in all different ideas, not just the baseline model. So for all 5 ideas, the corner plots follow the same trend. And here again, we have the violin plots. So each color corresponds to a different idea, and each idea has a pair of them. The first one without the residual and the second with the residual. We see that in cases there is improvement of 1 order of magnitude. And so the red one corresponds to the baseline model, like introduced by Kahn and Green. And then the gray corresponds to the first group of ideas, which included an extra input parameter. And then the orange and purple one correspond to the augmentation idea. And finally, the blue one and green to the dissection of either the input or the output. So to sum everything up, both learning and physics-induced ideas are useful for the improvement of training results when building a surrogate model, and also the presence of a residual errors network aids the final results and mismatches. And thank you for your time. Here's the list of references that I used for my talk.
Thank you, Stella, for your talk.
Thank you.
Does anybody have any questions?
Can you hear me?
Yes, I can hear you. Yes, yes.
Interesting ideas in there. Could you explain a little bit the input and output augmentation? I didn't really understand what you really do with those steps.
Okay, so let me repeat that. You want extra information for the augmentation ideas, right?
Exactly.
Okay, thank you. So I have a little an extra appendix slides. So we have the input augmentation is the doubling of the training data set. So we have a branch which corresponds to the log of the mass ratio Q, and then we insert an extra branch with a minus log of Q. So we have to, then the samples go to 400,000 samples, and we have separately because let's say because the nodes are also doubled because its branch correspond to its own nodes. We then have the mean of the predictions from the 2 branches to get a single a single prediction from the two branches of the network. So the training happens in a single network, but the branches are separate from one another. And this is for the input. And for the output, it's here. So like I said, the output nodes, we have the coefficients from the empirical interpolation. So we thought that it would be a nice idea to have the network to predict not just the coefficients, but a function of the coefficients. So if the initial coefficients, let's say, is y, then let's say that we need the network to predict the 1 minus y. So like I said, it's like following different paths to reach the same destination. So again, we had extra output, but this time in, an extra branch, but this time in the output. And again, we had the average between the predictions to get the final predictions of the network.
Okay, thank you.
You're welcome.
Any other questions? I actually have one question myself. I think you're using for error as a loss. So is that the case?
Sorry, can you repeat?
Yeah, so I think you're using mean square error as a loss.
Yes. Mm-hmm.
Okay, because so from my little experience, actually, sometimes mean square error might not be the best loss to use. So the thought by using some other type of loss, like for instance, bus system distance or any other metric. So it was a question. So do you try to use other type of loss to improve your results?
No, we did not. We just stayed we stick with the mean square error of the training.
Okay, well maybe it might be.
And also the final mismatch. Okay.
Ah, right. Yeah.
Yes.
So maybe
so we had.
Useful.
Sorry.
Sorry. No, go ahead.
I'm sorry. So we had like a double check. So the first was the mean square error from the network itself between the comparison of the predictions and the ground truth. And then after we constructed the waveforms, we then had again an extra test by measuring the mismatch from the reconstructed waveforms. Okay, so we thought that these two, like also Khan and Green, they perform in their work. We thought that these two were enough to make final decisions.
Okay. Yeah. Indeed, mismatch is very good comparison for sure. I was wondering only in the training phase, like maybe using some other type of loss could also improve even further your results. But this is maybe an idea for future work if you have time or energy. So
yeah, that's right.
Good luck.
Thank you.
So any other final question? No, then we give a big applause to the speaker once again.
Thank you very much.
Okay, so I think now it's time for the other speaker.
Switch here. Press this. Okay. Oh, it's already on. I have this one.
Let's share the screen.
Okay, so
Share the screen. Share. Yeah, select this. Let's hide this. You stop.
Sorry for the delay. Yes. I was it was working until some point.
I keep So we
This
can
is
hide
this way one.
this panel. Yes.
Yeah,
You know,
ocultation.
yes.
Then,
Now it's
And then Control L.
yeah. I think
Oh, sorry.
No, the kitties.
that's a spoiler.
Spoiler alert. Okay. So you may use this microphone if you want.
Yeah.
Connect it. Good. Good. This is a laser with
Okay.
button and stuff.
And that works too.
Okay, so our next speaker is Ivan. So whenever you're ready, go ahead.
Yeah, I'll never be ready, probably. Okay, hi everyone. This is going to be a bit different from the rest of the stuff that you've heard here. So first of all, I made the presentation in PowerPoint and not in LaTeX Beamer. And second of all, I'm not a physicist, so I will be discussing more like machine learning, signal processing stuff. And I hope that it will be, well, interesting to you. Okay, so first of all, the title of my topic is Intra-domain, cross-domain transfer learning. Now, I believe that you're already familiar with the concept of transfer learning. So the idea is to learn from one type of domain. Okay. So the idea is to learn from one type of domain where you have abundant data. You learn useful features, like parts of feature extractors that you can then apply to another domain where the data is not so abundant, and then hopefully improve the performance of your predictive model. So this is something that we did. We did it basically, this was a collaboration with people from IMGV, so seismologists. So the stuff that I'm going to be talking about, the results that I will be presenting will be involving seismology data, but I'm hoping, so I believe that it can be to some extent translated to gravitational wave data. Okay. So first of all, the introduction. Deep learning models require large data sets for successful training. So if you want to model, if you want to build a predictive model that is capable of dealing with highly nonlinear stuff, so if you want to model highly nonlinear distribution, then you need a lot of parameters. And to account for that, you need also a lot of data to make the model converge. What happens if you don't have enough data? Then you need to search for alternative options. So deep learning is one especially interesting type of models tied to machine learning, which helps us build both feature extraction and classifier or regression model simultaneously. So this is a simple example of an image processing pipeline, where first we do some feature extraction, and then we use a predictor. So for example, you just only use like a fully connected neural network to make a prediction. So is this a photo of a cat or not? The use of feature extractions, so feature extractors are commonly used to make the problem of classifying simpler or regressing, so making the prediction simpler. And basically this part of the model deals with the high variability of the data. So what we want to do with this, we want to make an embedding in a latent space and then proceed with work with that. Okay, so this is it. So the general idea of transfer learning is to try to do the one of problem. So let us say we try to learn some kind of concept in a simulated world and then translate it to a real world problem. Okay. So it is one of the possible ways to overcome the problem of using small data set when you're trying to model a complex problem. So what we do, we transfer knowledge in on one task and use it on another task where the data is not as abundant. Hopefully making the training possible even for the target data set where the amount of data is not as where the amount of data is not as big. Okay, and apart from making it possible to converge to a meaningful solution, we're also hoping to make the convergence of the model a bit faster. So the research questions we ask ourselves is first, how transferable is the knowledge between domains. For this purpose, so we had two sub-questions. One was intra-domain learning, meaning if you use domains of data that are similar to one another, and what happens if you use cross-domain learning. So you learn from one type of domain, and then you transfer it to something completely different. So with this regard, we use the definition that intra-domain means sampled from the same type of underlying process. So data sampled from the same type of underlying process using the same propagation medium and measured using the same kind of measure instrument. And cross-domain is, of course, okay, so cross-domain is everything else. So we had 3 data sets for intra-domain tests and 3 data sets, or rather 3 plus 3 for cross-domain. So we had several data sets, and in addition to that, 1 audio, 1 medicine EMG, and 1 financial stock market index data set. So we were also interested in we're also interested in the fact that we're also interested in how does transfer learning affect the convergence of the model, and how does the target data set size affect the performance of transfer learning. And for this, we used 2 undersampled data sets, so one of size 1500 and one of size 9000 training instances. And we compared the results obtained with this against the reference model, which was built only on these data. So we call this like training from scratch, but it is basically training from randomized parameters. So no prior knowledge is being involved in the model. Okay, and also we were interested in seeing how does the choice of a model impact the performance of transfer learning. So this is later presented in the results. Okay. So the experiment is we have a raw waveform. We use convolutional layers to extract the features on raw waveform data, and then we use those features to transfer it to another model, or rather, we use the same model with those features, but we use other data to fine-tune the model and then hopefully get a better result. So this was a fairly large experiment because we analyzed 6 data sets. We analyzed 4 types of model architectures. Some were tied to seismology data sets, some are like general time series data processing models. And we were also inspecting those 2 undersampled data sets, target data set sizes, so 1K5 and 9K. The reference model that is being mentioned here is basically the model that we trained from scratch, okay? So we use only this small number of data to train a network, to train a predictive model from the undersampled data set, and then compare it to the same thing, but using pre-trained weights. Okay, so the summary of the experiment is then using 4 predictive models, 6 source data sets, 6 target data sets. Of course, we wouldn't do the source and target of the same data set because that wouldn't make sense. But this, and also, we also had 1509K training instances. So this actually gave us 60 pairs of domains to examine. We also reran the experiments multiple times so statistical tests could be applied. Okay, so this is a list of the data sets and of the models that we used. So first 3 data sets are from seismology, so LAMEX, LandDB, and STED. So the second and the third are well known. The first one is ours, so from the collaborator on the paper. And these are publicly available data sets from other domains. We'll see a review of those on the next slide. And for the models, we actually used 2 seismology models, so 2 models that were originated from seismology papers, and 2 general purpose time series data analysis models. So temporal convolutional network and multivariate LSTM fully convolutional network. And those were, okay, magnet and convex wave, INGV, they don't mean, okay, they're not acronyms, so it's fine. These are rough sketches of model architectures. So what we did, we basically took several model architectures that looked promising. We did minimal tampering with them. And the only thing that we did, that we had to do, was adapt them to the target domain. So the training, so the knowledge transfer domain, the original domain, and the target domain, the source domain and the target domain. And also we had to account for some things like this factor streamx, which was used in some models, and we had to add it to others as well to make the comparison fair. So streamx is actually a parameter that says what is the amplitude or what is the highest value in your signal. Okay, and this is kind of fed into the fully connected layers later on. So you do the feature extraction bit here, and you just append this value, and you stuff it into the fully connected part of the network. Okay, so this is the layout of the data sets we used. Okay, so you can see that they are quite different. And even if we are talking about the domains, even if we are comparing the domains that originate from seismology, the data that you get here are really different. So just if you use the same kind of frequency response, so same kind of signal, and you stretch it over a longer patch, over a longer time period, then the features that you use to extract the useful stuff for one model will most probably not be working for another. Okay, so we didn't have an idea of what was going to happen, but fortunately we got some good results in the end. So for the EMG dataset, okay, so I forgot to say, so speech. So the first three datasets are originating from seismology, and they are basically used to predict, either do an early warning or predict if an earthquake is happening or not, or predicting magnitude of the earthquake at epicentral location. The last three ones, so speech is actually classifying the spoken word. So you say a word and it falls into one of 35 classes or so, I think. EMG is measuring muscle movement using a wristband, and you do pinching motions and try to classify which one happened. Okay, so we didn't use the original maximum number of channels. We used only 3 instead at equidistant locations to get the best measurements, but this was used to be more simple. And S&P 500 is of course the stock market index prediction. So what will be the value on the next day after a sequence of 50 days? So on the 51st day, what will be the index value? Okay. So what we did, I need to say something about the evaluation matrix that we used. So we basically measured accuracy for classification models. It was weighted F1 score. And also we measured convergence rate. Convergence rate was calculated in this manner. So basically we took a fraction, so the ratio of the area under the curve, which projects how well do you perform at each epoch, divided this by the area A, so this integral here. Meaning that models that would converge faster, so that would be better faster in earlier epochs, would get a better score. And the same thing we had to do for regression domains. So here the thing is that the accuracy measure is reversed. So we were using mean absolute error, the L1 error, because it made more sense. And here again we use this ratio, so this and this, to get the idea of how fast the model is converging. Okay, so this is the basic layout of the experiment. So we compare models that are learned from scratch, okay, from randomized initializations of weights against the models that are using prior knowledge and are then fine-tuned on 1K5 or 9K data. And we rerun this 7 times to account for the for the chance in the experiments. Okay. So these are the results, some of the results. If we are looking at general applicability or usefulness of transfer learning, then this is the first view, which is using all the data sets simultaneously. So we can see the blue thing represents transfer learning wins. The red thing, red bars represent non-transfer learning wins or transfer learning losses. So basically, in terms of accuracy, so both classification and regression, you can see that you gain a significant improvement if you're using. Okay, there is a high chance that you will get an improvement if you're using transfer learning. Much to our surprise, convergence rate was not as good. So of course, here we also got some pretty good results, but compared to the accuracy gain in the number of wins is actually quite worse. And the overall results are like this. So you basically have a 91% chance to get either better performance and convergence, or either better performance of your model. So it can pay off to use this kind of approach. Okay, so these are the results in a bit more detail. So for each row and column, you get a result that is the average over 7 reruns over for 4 model architectures, and if so this is the relative improvement in model accuracy over the reference model. So the green stuff, the green fields are means we have a statistically significant improvement, and the red fields as well. So here we can observe negative transfer, meaning that by using a pre-trained model, we actually got worse results. And here the results are inclusive, so if there is no color involved, then we account this to chance. So in general, the results suggest that you can get really pretty decent improvement. The details of this are described in the paper, but we can also discuss them if you're interested during the break. Okay, so I will not go into any further detail concerning this. These are the results on convergence rate. And again, here we can observe a bit less significant improvements. But yeah, okay, that's it. And overall, if we are comparing the 4 models that we were using, these are the results. So there is no best kind of model that you should use on one type of problem or the other. So basically, the conclusion is that you need to inspect different kinds of models and test them under some circumstances to decide which one would benefit you the most. Okay, so I forgot to mention earlier, there was one parameter that we did fiddle with that has proven to be quite important for transfer learning. And this is the ratio between the learning rate of the fully connected layers and the learning rate used for the convolutional layers. And we made a decision to arrange this from this value to this value. And here you can see the of each value of the learning rate multiplier on a specific model architecture. So the higher values, so for example, Conway, Quick, and G, suggest that using a learning rate multiplier, of this magnitude is the most beneficial, and if you increase this, then model performance deteriorates. It is quite uncommon to use an inverse value of an inverse size of multiplier. So normally, what you want to do with transfer learning, you want to preserve the learn features at the convolutional layers and focus on optimizing the classification or regression layers, so the fully connected layers. But we discovered in our experiments that for some models and for some data sets, it actually does pay off to make the learning rate as a feature extraction part of the network higher than the part on the fully connected layers. Okay, so to summarize, we found out that transfer learning is very likely to get a better performance score, or at least as good as the model trained from scratch. So you saw in the results, you get basically roughly 75% chance to get a better performing model, and the 64 something percent chance that your model will converge faster. Even seemingly unrelated domains can be mutually compatible enough to yield positive effects. There is no symmetry. We know there's no symmetry in knowledge transfer. So, for example, if domain A was proven to be beneficial for transferring knowledge to domain B, it doesn't necessarily mean that you would get the same effect if you did reverse the roles of them. Okay. So the main message would be to if you're dealing with data sets of limited size, it might pay off to try to use transfer learning, even from a seemingly unrelated domain. And if you're doing this, you should probably play with the parameters, with the hyperparameters of the model before saying, yeah, this works well or this does not. Okay. Now, I have no idea if this should work on gravitational wave data too, but depending on how much instances you have and what kind of problems are you trying to solve. Okay. You can read this in the paper that we published recently, which is also available on arXiv. And if you want to repeat the experiments, it's here. So all the code is there. So if you want to use it, you're free to do so. Okay, that's it for me. Thank you.
Okay, thank you so much, Fred. And does anyone have any questions?
Very interesting. I have one serious question and one less so. The not serious question is you have great performance going from seismology to the stock market. So why aren't you a billionaire retired yet?
It's really chaotic. So I wouldn't. Actually, we chose this one because it is quite stable. It's not as unpredictable as real stock market. So if you want to use this as operational information to make investment, yeah, this is probably not very good. Yeah. You want to use something that is more chaotic, yeah, but
Maybe.
But you're not flashing, with your money.
it's a possibility.
That's a serious question. So when you do your transfer learning, do you only swap out the input layer to account for the different size, or also several layers? Because I've seen some people who basically only keep the middle part of the network and get rid of several layers at the start.
So actually, we fully replicated the architecture of these networks. The only change that we made was in the first layer and in the input layer and the output layer. So the output layer was, of course, needed to be adapted to either regression or classification, because we used. So this is originally, I think, a regression. No, so actually this is a classification model originally. But if we wanted to do regression with it, then we would change the output, which was a softmax layer. We substituted it with only a single neuron with a linear activation, and that's it. Okay. And for the inputs, we actually had to adapt them. So from one channel to 3 channels. And if the originally it was 1 channel, then we added 2 more. Okay, to the input, I think. Yeah, and if it was originally 3 channel, then we just replicated 1. So we use the same input 3 times, which should also in backprop lead to different rates, but yeah, hopefully.
Do you think there's ever a benefit to also reinitializing the first 1 or 2 convolutional layers if there may be 2 burnt in already on the original model?
Well, we didn't expect that, but I don't have any experience of such thought. Yeah. So this problem was quite large, and we had to limit it to some extent because it grew quite. Yeah. So every parameter that you think of fiddling with makes the problem times something. So yeah. Okay.
Oh, thank you. Very good talk. Let me try first to answer the question why somebody is not millionaire if he knows to do with MCU, because this is non-commercial research.
Of course.
Okay, so I have actually a couple of questions. The first one is, can transfer learning help us to decide how two data sets are similar? Are they similar? If we take two identical data sets and we apply transfer learning, we do not expect any changes, any benefits, or
Okay, so
better, not worse results.
So assuming that you have like two data sets that are sampled from the same underlying distribution, so that would generally mean that they are like the same or maybe very similar. Yeah, I would expect that there would be no. Yeah, actually, you should. This is not a scenario that we inspected here because this would mean that we would, for example, use speech data set and then fine tune it again on a subset of the speech data set, meaning that we just strain everything from the entire amount of data instances that we have. So I don't expect that we would get an improvement. But of course, if you, for example, want to see if you get an improvement in accuracy, you can plot always the learning curve and see what happens if you use a subset of the data. And eventually, if your model is like expressive enough, you will get to converge to the limit, to the irreducible error. So something that you can't learn a model that performs better than that because the data is flawed. Okay, there's some noise buried inside, or you have measures that are inaccurate, and then you just have some kind of an error that you cannot solve in any way. So to get back to, okay, I drifted a bit here. So to get back to the question, to the original question, I have no idea. The similarity of this experience.
I'm asking because we had the first day, I think we had talk with Daniel de Aquila about applying speech processing techniques to detection of gravitational waves.
Mm-hmm.
Which means that we are using these speech data sets and speech algorithms on the other side, and on the one side, and on the other side, the gravitational wave data sets.
Mm-hmm.
Can transfer learning help somehow to bridge between these two disciplines, or somehow upgrade this discussion?
So the data the results that we present here support the hypothesis that you can get a useful you can benefit from doing this. So here we, for example, do seismology, so learn from a seismological data set and then transfer it to so from the data set and then transfer it to another data set. So for example, we have here we learn from let's say we learn from speech data set, so from audio data set, and then we transfer this to seismology. And if we use a data set of 1,500 instances, we get this much benefit on average in 7 reruns using the best valued hyperparameter for the learning rate multiplier, blah blah. If this is a relative increase, so if you can get this much, if your original model using only, let's say, gravitational wave data, performs this worse than this one, then you get a significant benefit. But you should actually try this using your.
Just a short question. Could you please just elaborate a bit about the measure of accuracy that you're using? Because today we had also touched this point. So in relation to this efficiency that was mentioned today.
So accuracy, so we have two parameters, the model accuracy, how good the model is at predicting something, you have F1 score for weighted F1 score for classification measures. So if it were a binary class problem, then you would just have the F1 score. But this way, we use the one versus all principle. So if we have, for example, for the speech dataset, we have 35 pluses, and you say, okay, so the first word is a positive. We use the first word as a positive, and all the other 34 as negatives. Calculate the F1 and weight by the frequency of occurrence in the test data. Okay, so you use all this, you divide by 35, and okay, so now it's actually weighted. So okay, you get an average. Okay, that is related to the frequency of occurrence. And for regression, so if we predict a real value, then we use mean absolute error. So just the difference between the predicted value and the ground truth. Okay, but without the sign. And convergence rate is a ratio of the area under the curve and the rectangle. So we needed, why we didn't use only the area under the curve, because it would actually penalize models that converge faster. But this way, if something converges for a longer time, you get a larger area here. But if you divide it by the rectangle surface, then it's relatively worse than this one, which is like performing better faster in a few records. Yeah.
Thank you.
Yeah.
Thank you. Any other questions? Well, actually, I have one very quick question myself. I think transfer learning and curriculum learning have the same problem in a sense, or at least that's what I read. It's just that when you transfer from the source to the target, you might forget the source. Did you observe that? And if so, how can you take this into account?
Well, sorry, I didn't understand. So I'm actually not familiar very much with curriculum learning.
No, but in transfer learning, you have the source, data set, and then you have the target. So when you transfer from the source to the target, so you are very good in the target, but you might forget the source.
So this is a one-time shot. So we learned the model from source data set, and we are not interested in any way anymore about the data. So we just use the features, and the features from the model encode the distribution from the source data set. And then we fine-tune those parameters to fit the narrative of the target domain.
So you never went back?
No. Okay. So these are actually, so the results that you can see here are actually independent runs. So each of these numbers is completely independent of the others. So for example, if we want to do this here we go from speech to Lomax 9K, and we get this. And here we go from Lomax, so the entire data set, to speech 9K. So these two experiments are completely independent.
Yeah, thank you so much.
Yep.
And another applause for the speaker. And I think now we have discussion, right?
So thank you very much. Now we have a few minutes before lunch to have a final discussion of these two sessions and also about other sessions. Is there maybe some sort of a comment or question from the remote also? You're very welcome to join. Some comments, some questions. If not, then maybe I will want to comment on our offline discussions about the G2Net paper. I know that other groups are planning to write their papers at the end of the action. I think our group is not really planning to write a gw1 paper, but we'll join this G2Net paper. And the idea that basically emerged after our discussion was that basically there are two options. Either we do something more complicated or less complicated, and less complicated thing is a necessary part of the more complicated thing. And this more simple thing is just to write a review of what we did. Once we have it, we can decide to write a more sophisticated part of Outlook, what worked, what didn't work, this type of kind of summary. But so far we need to focus on writing what we have. We have several things already kind of marked in the overleaf. I have to just sit down, coordinate this, and write this as soon as possible. And then we will be, well, we can then decide whether we are happy with this or we want to do something more. That is this type of analysis of the whole prediction, kind of what we can do in the future with what we did already, and so on. So this is our plan, at least from the point of view of the working group 1 so far. And we'll be working on this, and of course, the other working group members and members on the remote side also are can be invited to participate in discussion of this. We can do it on kind of on the email basis, or we can have an ad hoc Zoom meeting to discuss this. Are there some other comments or questions? Yeah.
Yes, so if I understand that this is the last discussion that you have today, after this it is a closing, right?
This is the last official discussion session, and then of course we'll have some unofficial meetings also.
Unofficial, this is like official closing of the meeting.
Yes, so we will be closing before lunch. Yes, indeed.
Yes.
This is the last time. This is the last moment when you can say something officially.
I do not have a mic after this session, right? You guys possibility for me to talk. Yeah? Okay.
This is your last chance.
Yes, okay. I just wanted to share my impression that this was really excellent meeting, excellent workshop. And I would like to thank a lot to ESA in the first place, our host, and all organizers from University of Valencia, and of course to thank Michael for making this great event.
Let me comment. Thank you very much for those nice words. So first of all, I didn't do anything. That's the thing. Yeah, so big thanks and a round of applause to Samuel and to Isa, who were basically managing this nice connection to the remote side, and everything was very well organized. So thank you very much for the organization. And yes, so I'm very glad that we met. That was a very nice, diverse meeting. A lot of interesting talks. You might, I already said that, but you might think that someone was thinking about the order of talks, you know, that they were kind of putting the order and kind of everything kind of fit nicely. It was completely random. But as you can see, we have all kinds of interests that are really mutually kind of common. So you can put talks completely at random, and in general, we would have some sort of overlapping areas, which is really nice. I really like this, that one talk ends and then the other one starts, and then there's the same thing going on. So it's nice. All right. So let me officially close the meeting, and we can go for lunch, and then we can, of course, then continue discussions and hopefully meet soon again at some point. Thank you very much.